There's an article a student sent in just now. They hacked the unemployment system by hacking the debit cards. So it's not obvious. Now they say there are red flags and Bank of America should have caught it. But anyway, I don't know. I do know that credit cards are not very secure at all in America unless they have the chip, and they don't all use the chip. So that all the security is done at the bank side where they detect suspicious transactions. And yeah, I can see why this would not get caught. 2 suspicious withdrawals, one for 200, another from 800 from Milpitas, when in fact this person is in like the South Bay. I can see how that's not enough to trigger the traditional suspicious transaction flag. I think they normally look for like transactions from China or something. But anyway, it's certainly an issue. If those debit cards are getting hacked, that they're going to have to deal with that. Anyway, here's another study. This is based on a similar study a few years ago. These guys went through the TCP/IP stacks for several Internet of Things operating systems, and they found that a whole bunch of them use 4 stacks, and those stacks have serious vulnerabilities like code execution and other ones. So a whole series of products are based on this, Light OS and FreeRTOS and so on. Many, many products use the same stuff. So this is basically a dependency problem and a supply chain problem, which is all the rage these days. If you actually use somebody else's software in the form of libraries you import, then you don't really know what you're getting, and you don't really know if you have the latest version of it and all that. So this one hit the news just a few hours ago. Red hot, FireEye got hacked. The CSO was talking to us just last night, although he didn't mention this, which I am sure he's not allowed to. I mean, when a thing like this happens, you don't let random members of your company deal with it. You have a very careful statement, run through lawyers and everything. You don't let random people from your company say anything about it. But anyway, FireEye got hacked. FireEye is the main incident response company in the world. They pretty much invented incident response. And what they got stolen was their red team tools. For some reason, they have red team tools that are they've gathered from malware, and they say they're not 0 days. But anyway, what they've done in response, which seems pretty drastic, is they have burned all their own tools. So they have now publicly released all the indicators of compromise to detect all of FireEye's red team tools, so that if the people that stole it attempt to use them, then you will easily be able to add them to your Snort and other software to block it. So that seems like a very responsible thing to do and a very expensive thing to do. I would think that means FireEye is going to have to update all their red team tools, but anyway, that's what they did. So FireEye does not say who hacked them, but some newspapers do. New York Times says they were hacked by a nation state, and the Washington Post says it was Russia. They say it was Russia. They even tell you which APG group it was. SVR, which is APG 29, Cozy Bear, the same people that hacked the State Department and the White House during the Obama administration, and the ones that hacked the Democratic National Committee during the last election. So, I mean, the 2016 election. So I don't know if all that's true. Certainly FireEye didn't say that, and these people are talking to other people, and you don't know how reliable it is. But anyway, that appears to be the case. The Washington Post is also bold enough to blame the similar group for the hack of NSA's attack tools, which is again something. I think there's different levels of confidence. Different newspapers make judgments of whether it's time to attribute something. The really closer to government things are more reluctant to do it. Anyway, so that's what they did. Somebody posted this, which is kind of fun. 10 years ago, in 2010, they checked for the space shuttle's retirement, and they found that they are not handling their equipment correctly at all. They are not sanitizing things. They are not cleaning up stuff they're throwing away. And one of the fun ones was this. They found hundreds of hard drives just thrown away in a dumpster marked cables only that's wide open and not locked. So anybody could just steal them. And anyway, so that was true 10 years ago. Maybe it's better now, and maybe not. All right. Anyway, this one is kind of amazing. This game called Cyberpunk 2077 apparently has some kind of deliberate epileptic seizure-inducing flickers. They found they have in fact taken, there's a pattern of lights that is used by medical professionals to trigger seizures for medical tests, and they built it into the game. And then they say, oh, somewhere in the terms of service says don't play this if you have epilepsy, but you know, that's pretty incredible. There were a few movies and games that had a risk of this, and they were worried about it, but this does seem very outrageous, like kind of thing you could get sued for, and maybe they will. Anyway, let me see if I can. All right, good. Anyway, so that's various people are getting upset about that. And why is this not closing? Right, just a moment. All right, that's working. Why is this not working? Huh, all right, oh, there we are. All right, so this sounds very interesting. Cloudflare and Apple have together designed a new privacy-preserving internet protocol, which will improve DNS. Now, the original DNS that most of us, I think, are still using sends unencrypted UDP traffic to resolve domain names to IP addresses, and that announces to everybody on your network exactly where you're going all the time, which is pretty rude. So the most common solution is now DNS over HTTPS or DOE, which sends all this sort of HTTPS connection. But now they've made another one called oblivious DNS over HTTPS that they say is even more private. So they don't give you a lot of details, and you can't practice with it yet because it's not built into any browsers. But apparently this is considered the next step in improving DNS queries to make them more private. So I'm very interested to check it out once we get it available. Now that they've defined it, they say they're already allowing proxies, allowing for early adopters to begin using the technology. So presumably somebody will put this in a browser version and we can start playing with it. We'll see what happens. I'd like to at least catch it in Wireshark and take a look and see how private it really is. And someone posted this on Twitter, which is news to me, the DFY Diva, disaster, digital forensics and instant response, had a whole bunch of free workshops on all kinds of good products like Zeek and defending serverless infrastructure and so on. So this is pretty good. Lots of good workshops. Some of them cost money, some of them are free, but it looks very good. Anyway, a good resource. There is a one credit sheet. Yeah, there is. Yeah, that's right. And so I don't know how much of that stuff he's had. I taught that course for a while. Now Alan's teaching it, and I think he's doing a fine job. But there are these, DNS security is pretty hot. Yeah. Yeah, I think we're the only college that has that class. Dan Kaminsky was going to visit us, but he was too busy. Anyway, so there's this company called Affirm, which is apparently considered a big hot firm. And if you go to buy something stupid like this, the world's first smart coffee mug for $130, which is kind of hilarious in itself, as to why you need to connect your coffee mug to the internet is not clear. Yeah, good. You took the course, it was good. Yeah, that's good. Yeah, I think it's probably using the labs I wrote, that's why. Anyway, so but yeah, Alan is very good. Anyway, the point is when you buy this thing, shop now. Okay, there. You can pay $130 now, or you can make 3 payments of $44. Oh, now the last time I looked, it was 3 payments of $40. Oh, that's right. That's right. So the point is, this is Affirm. They let you pay everything in payments without having a credit card. And it seems to me that it just totally duplicates the function of a credit card. But when I read through the business model, basically what they're doing is it's just like Uber. I mean, they're already taxi cabs. The reason why Uber is successful is because they've taken a lot of the corruption and extra expense out of taxi cabs. So they have a good app, so you see when they're coming, and they are often cheaper and such. And that's what these guys do now. It's just a cheaper, simpler form of a credit card. And the thing they say is their business model does not depend on dragging you deeply into debt. So you spend your whole life paying off interest. It's quite the opposite. You have to pay it off. And if you don't, you can't use Affirm anymore. And apparently that's all the punishment. So they don't care if you pay late, but you have to pay. And apparently if you fail to pay, they just refuse to let you use Affirm again. And they say this is extremely popular. They take a percentage from the merchant to do this. And they say merchants find like 85% higher purchase when they have this option here. and they have to give a firm like 10% of it, and they find that to be entirely worth it. So it's very interesting. It's just somewhere between a credit card and a payday loan, but apparently it meets a real need. Anyway, so let's go on to the slides for today. This is the last class, and I just thought I'd introduce this topic, which I think is fun. All right, so anti-disassembly. Mentioned this before. The disassemblers are not perfect. They make assumptions. So the point is you can create specially crafted code that will mess up your disassembler so it lies to you. And this will require the disassembler to have a higher degree of skill. And as I mentioned throughout this course, the whole point of malware is to scramble the code to make it harder to understand. So, all right, disassemblers typically assume this. Each byte can only be part of one instruction at a time, and it doesn't waste any space. That's the way compiled code is if you use something like a C or Visual Basic compiler, but you don't need to do that. I used to write self-modifying code years ago in assembly language, and you can violate these rules, but if you do, the disassembler is not going to figure it out. So here is a jump instruction that's going to jump to this location +1. And therefore, the first byte here is not used, so this is completely wrong. The disassembler started disassembling here and assumed the first byte was part of the instruction. So that's linear disassembly, where it just takes every series of bytes that forms an instruction, and when it's done, it starts with the next byte and disassembles that, and the next byte and disassembles that. That's called linear disassembly, and that is pretty easy to fool. So what you use is a flow-oriented disassembler. When you have a jump, it follows the jump and starts disassembling at that point. Even if it's skipping something in between, it just decides that must be data. So it turns that into a byte of data and gets down here. So flow-oriented disassemblers will succeed, but the problem is they are not very smart. They will notice a hard jump like this, but as we'll see, there are a bunch of similar instructions that they will not recognize as time to switch to flow-oriented disassembly. So here's the game. So linear disassembly just assumes that you have code packed densely with no gaps between them. And so you can make code here that does, this is the code that does it. You just keep moving forward, skip a few bytes and go to the next one. This is a real disassembler. They just take a series of bytes and then they start at the next byte for the next instruction. This would work for code that was made with a compiler, which is of course the way most people do it. But if you write your own code in assembly or modify it later, you can confuse it. So that's the game. It disassembles every byte. All right. So here's, you can have a case instruction, or a case is a multi-stage if, where you have a bunch of different jumps. And then here's an offset table with a whole bunch of addresses. So you'll have a list of pointers. This is data, not instructions. So if you were to have a linear disassembly doing this, it might try to disassemble this stuff and turn it into instructions when it's actually data, which would be another flaw. Yeah, it misinterprets that stuff as instructions. All right, and then there's call. Call is a way to enter a subroutine. So it's 5 bytes long. You have an E8 followed by a 4-byte address. And so if you put extra E8s in places, then it will chew up the next 4 bytes and totally mess everything up. That's a pretty good byte to add. Add an occasional E8 you don't need, jump over it, and the assembler will screw up everything from that point on. It's disassembler. All right, so FIDA Pro uses flow-oriented disassembly. As we said, it doesn't assume that all the bytes are instructions, and it doesn't assume that no bytes are skipped. It examines the instructions, and it finds a list of addresses to disassemble from things like jumps. So if I do a jump 0 to this point, and push and call and jump to location 1D, then it looks at the JZ and it says, okay, start disassembling at location 1A, and it looks at the jump and says start disassembling here. So it will disassemble code starting at each location that you jump to, assuming, well, that must be code, so let's start there. And it doesn't care if there's what's in between. So that's a pretty good arrangement. It sounds pretty good, but a linear disassembly cannot do this. A string in the middle of data will foul it up, so it will misinterpret things. It'll interpret this string failed as instructions, and then it will get everything wrong from that point on. Right, so here's things that cause trouble: pointers, exceptions, and conditional branches. Let me just check where's my cahoots. There they are, good, okay. All right, so conditional branches have a jump zero, jump not zero, something like that, where it can go two places, a true fudge and a false branch. In compiler generated code, they would work the same, but they can have different disassembly. So let's take a look at those disassemblers. Do the false branch first. So here you do a call. So you call to this location, then you do a pop and a return, and the return will put a pointer to hello in EAX, because return pops the stack. Okay, return takes the element on the stack and jumps to that location. So here I did a call and I did a pop. Let's see, put your pointer to hello in EAX. That's the return pointer, right? That's right. And so, see if I understand. It does a call near here. Here, where's the push? That's what's confusing me. It interprets this as a push, but it's not. Oh, I see. Then it does a return. All right, I'm not quite understanding how this works. Somehow it mixes up this instruction. It looks like text, but it's interpreted as a push. I don't quite see how it ever gets the push done. All right, this one I don't understand, but we'll go on. I think I figured out some of the others, and I thought I had this one, but I cannot understand it right now. Anyway, so you can clean this up. Just tell it that this area is data and tell it that that is code. So certainly the part where it misunderstands this as a push, I think that might be all the point is here. I thought it might do something more interesting than that, but I think the only point of this is that it jumps over that stuff, jumps 6 bytes forward, and therefore this string with a null terminator is not a command, but the other disassembler interprets it as a command, that's all. Okay, does a call do a push? No, a call does a pop. A call takes the value on, let's see, a call. Well, a call might do a push, you're right. It's the return pointer, right, it's the return pointer. That's right, puts a pointer next to EI, that's right. Thank you. Now, that's what I wanted, good. The point is when you call, it's gonna do it and it's gonna push this location onto the stack as the return pointer, exactly. So you go here and it puts this on the stack, that's gonna pop it off the stack. And that puts a pointer into, that's right, thank you, good. The call does a push, good. I appreciate the help. All right, so let's take a look at some cahoots, see how that works. Right. I guess that's it. All right, which kind of disassembly can be fooled by handwritten assembly code, but not by compiler generated code? Yeah, I guess I'm going to stick with you. I'm regretting this question. I think if you're smart enough, you can fool all of them, so all might be a better answer. But anyway, I originally thought of linear disassembly, but I'm sorry, that question is not entirely fair. Anyway. All right, what kind of disassembly is so stupid it won't even work correctly on compiler-generated code? All right. That's if they couldn't do that, they'd be no good at all. They can all handle compiler-generated code. All right, what does IDA Pro use? All right, flow-oriented, good. All right, and what kind of disassembler stops disassembling after an unconditional jump? Yeah, that's it. That's what flow-oriented does. After a jump, you stop disassembling because what's after it is apparently not code. So it can tell code from data in that regard. All right, so let's talk about some more techniques to confuse your assembler. You could have a jump if 0 and then a jump if not 0 going to the same place. And that, of course, is the same as an unconditional jump, but your disassembler might not be smart enough to realize that, and IDA isn't. So it doesn't consider this to be a 100% jump to that new location. So here's a jump 0, jump not 0 to some other location, and here's some stuff which it misunderstands as code when it shouldn't be code. Now, if you have, and notice it's jumping to 4011C4 plus 1. So it's going to jump past this E8 into the 58. So this address is going to be the address it actually jumps to, but IDA interprets that address as inside an instruction. So what IDA will do is turn the cross references to red, saying this really looks wrong. I'm jumping to a location, but that location seems to be inside an instruction, not at the start of an instruction. So I warned you that something appears wrong. All right, so you can fix it with D. You can take that byte and switch it to data manually, and then you'll get the right answer. You can switch things to data with D and for code with C in IDA to override its automatic guessing of what's data and what's code. All right, you can also have a constant condition, of course. You do an XOR to make EAX always 0 and then jump 0. So this is also an unconditional jump, but again, IDA doesn't recognize it. So again, you're jumping to this address plus 1, and IDA misunderstands and includes this byte in the next instruction when in fact it's jumped over. So again, you fix it with code and data keys, telling it what part of it should interpret as data and what part of it to interpret as code. All right, so these use an extra byte, and you can ignore the extra byte. That's what we did here. You can also reuse a byte. This is almost as crazy as self-modifying code. You can use a byte twice. So here I have a jump -1. That's an FF. And a jump -1 will go back and now execute starting at the FF. So here the FF is the argument of a jump. Here the FF is the instruction for increment. So that is some code which cannot be simply linearly disassembled. In fact, it's not as simple as there is one instruction for every series of bytes. This byte is used in 2 instructions. So no disassemblers that I know of are ready for that. And here's another one. All these dark colored things are used twice. So you move something, do an XOR, you do a jump 0 back to here. Now some of that is mixed into this command. You know, it's kind of madness. Anyway, here's a fake call. Here's real code. Anyway, you do a lot of, you can clearly write snippets of code that do these weird things, and the disassembler is not ready for them. So if you want to fix those, you can just knock out all the extra instructions and keep the only part that matters. That's one way to clean this up so you can understand it in the disassembler. All right. And so here's a function. at 4010C0, here's a function that does not much of anything, but the point is, I want to find out how many cross-references are there to this instruction. And here's one, 401011C0 with the actual address, because it's going to move into this location on the stack, that address. So that's a reference to it. But here's some more. Now that it's put it in a variable, it's going to call it by that variable name twice. And the calls by the variable name would require too much connecting of different lines for IDA to figure it out. So here, you're only going to find one reference when there are actually three references to that address. And so that's another easy way to hide things. You calculate an address, and IDA doesn't know what the address is at the time it is generating the output. All right, normally you do call and jump, but you can use return to perform a jump. A call is like a push and a jump. Return is like a pop and a jump. So here, I have a return in the middle, and that confuses IDA. But here what I've done is I've put this value on the stack. And when I return, it will find the value on the stack and go to a controlled address. So I'm able to make it go to a controlled address using return. And that, so second half is a simple function. All right. And so this pushes 401cc5 on the stack and then jumps there, because this call takes the current location plus 5, puts it on his return pointer, and jumps there. Adds 5 to the value DSP, and return will now jump over here. Anyway, that's the game there. You can just manually undo the convenience of call and return to trick them into doing a jump. All right, so again, you can patch this manually by substituting the bytes in IDA. And then there's the structured exception handlers, which we were playing with in the exploit development class. So you have this is what happens when you have exceptions in your code. You add pointers to routines that handle it, and then that goes to the next one. The next one, there's a chain of handlers. And if you don't handle any of those, it's an unhandled exception and goes to the operating system. So you can add an extra record to the top of this, an extra handler. So here, it adds something to the exception handler, which is up here at FS0. So it adds something there, and then it causes an exception. Here, it divides by 0. So the divide by 0 will cause an exception. It will then go to the exception handler. So again, you controlled the flow of code, but you did not do it with a simple thing like a jump. All right. And another thing you can do is you can confuse IDA about how big the stack frames are. It has to decide how many stack bytes a function uses. Now, normally the function prolog always does the obvious thing. It messes with EBP and ESP to make enough room for the local variables. But what you can do is you can make it where it compares something to 1,000 that's always going to be, this comparison will always be false. So it'll always do the jump low, and no, it will always not do the jump low. It will go here and jump over it. So it will never execute this instruction. But the presence of this instruction will confuse IDA, and it will say, oh, the stack has to be at least 104 bytes big to handle this command. So the stack is really very small, but IDA will misunderstand it and allocate too much stack memory to it. So it gives you a clue here how it really does quite a lot of assumptions in guessing to try to reconstruct what's going on with the code. All right, anyway, so here's the 15B. Yeah, good. Give it a few more seconds. All right. what technique is here? All right, that's it. Jumps at the same target. Good. All right. When would you do a divide by 0? Yep, to create an exception, so you can go to an exception handler you define. All right, and what technique is this? Yep, that's it. It's a jump, a conditional jump, but the condition is always the same. All right, which one involves altering FS0? That's the structured exception handler. It lives at FS. There's F and G stack segment registers. All right, which one is a clue that IDAPRO gives you to indicate anti-disassembly? The cross references turn red. Good. All right, which one involves declaring a large local variable in unused code? Yep, that's it. You will confuse IDA about how big the stack frame is. All right. All right, good.